So in our quest to try to find out if there's life on other planets, it's important to try to find these other worlds, these other places where aliens might live. So we've just started detecting these exoplanets. So since 1995, there have been a few hundred that have actually been detected and confirmed. So we're trying to look for places where these aliens might live. And like I said before, directly imaging them is very difficult, these planets, but indirectly doing them is a bit more easy. So I'm going to start by showing you the Doppler method. So that method, Doppler method, it uses what we call the Doppler effect. Now you might have heard of the Doppler effect as far as sound goes. This is something that you may actually know about, this effect here. This happens whenever a car, let's say, is driving towards you, and if the car is making a loud noise, let's say honking its horn or something like that, as it comes towards you, this is sort of a quick little diagram showing what happens with the sound. The sound waves right here are sort of squished here, so the length between the waves are short. But what that means is this is the key thing, is that as something comes towards you, this is the key thing here. So if it's towards you, you hear a higher frequency, which we call higher pitch. So that's the higher frequency here. And if it goes away from you, well then it has a lower pitch. So what happens then is this. If the car is going away from you, let's say you're standing here and the car is, let's say it's a police car with its siren, I think that's what this is supposed to be here. As it goes away from you, you should hear a lower pitch sound or a lower sounding sound. That's because a larger wavelength or a lower frequency. Frequency is what we think of as far as like if a sound sounds really high pitch like this, or if it's really low like this. You can tell I'm not a singer. There's a reason why I'm not. But we have a higher pitch or a lower pitch depending on if it's coming towards you or away from you. Which means that if we actually had let's say we did a graph. Let's say we did a graph. Ooh, uh-oh. But don't worry, this is not a math class here. So if we graph time on the x-axis here, and on the y-axis we put in the frequency. In other words, the pitch. So how high pitched something is. Well, what would happen is as something is coming towards you, let's just say right here, this is so that when it passes by you. So this is wherever you are here. So let's say you start the clock and it's driving towards you, and after that it passes away from you. Well, you would expect that the sound to be higher pitch. Whoops, it's supposed to be a straight line here. I did a bad job. Let me just go back here and undo that. So it's supposed to be a straight line here, like a higher pitch, and as it passes by, it'll be a lower pitch. You might have seen this when you've seen car races, for example. As a race car drives towards you, it's like, and as it passes by, now the sound doesn't actually go up in pitch. It's a constant higher pitch, and then when you passes by, it's a constant lower pitch. Now I've got a YouTube video I'm going to try to show you. I hope you can hear it. Let's just see if it works here. So this is a car doing exactly that. It's going to honk its horn. And then it passes by. So hopefully you're able to hear that. You can hear that the pitch really did change from high to low. Now this is an effect that you know, but there is an analogy. There is a Doppler effect with light. And this analogy for Doppler effect with light is as follows. If light, let's say a light source here, let's say this is the sun or a star or something, if it's coming towards you, well, like we learned before, if it has a higher pitch, that has a higher frequency. So I'm going to say here that towards you. Now, if it has a higher pitch, we also say it has a lower wavelength. So I'm going to say, lower wavelength means it's actually bluer. So we actually call it blue shifted. We're going to talk about this and why this is important. So the light will appear a little bit on the blue side. So it'll be a slightly lower wavelength, we say, or higher frequency. Now, if it goes away from you, and you'll see the reason why I wrote it like this right here. So if the star is going away from you, the light will actually appear what we say red shifted. In other words, the light will appear slightly redder. Now I'm going to explain a little bit more about this and why this is important, but a red shift of light just tells you it's going away. If light is blue shifted, it means it's coming towards. Now, this is kind of a weird diagram. This guy has really weird hair. I'm not sure what's going on here, but there's a good thing that I didn't draw it. It would have been a lot worse. So let's go through a little bit about how the Doppler method, or this is sometimes called radial velocity method. That's what RV stands for here. So radial velocity. That's what RV. Radial velocity method. So step 1, the orbiting planet affects the star. Now that we've explained a little bit about the Doppler effect here, let's explain how we can actually detect planets this way. So first of all, you have an orbiting planet and it actually affects the star. Most people think that an orbit goes like this. If this right here is the star, let's just say right here, this is the star, and you have the orbiting planet, a lot of people, including me, we just draw it as if the planet, let's say this right here is the planet right here, we draw it as if the planet goes around and the star remains fixed. But that's not the case, not exactly. Anytime you have an orbit, things going around in orbit, they both technically move. The good news is that the star is much more massive, so it moves less. So I have a little animation here I'm going to show you. This is by an amazing website called PHET. It's worth looking up. It's a project at the University of Colorado. Now, they have lots of really awesome free animations, and if you go to under simulations and physics and choose motion, there's one called My Solar System. So that's this one here that I've opened up. Now, very, very simply, I'm just opening up a simple situation of a planet going around a star. But look carefully. Although the planet orbits around the star, technically the star moves too, doesn't it? Can you see that the star is moving, the center one? So this is what we do. This is sort of the thing we're trying to detect, is that even though this planet is so far away and so dim compared to the star, we say, okay, we can't see the planet, no problem. Let's just assume the planet isn't there. So just imagine that you just can't see it. Now, you can't see the planet, although I said it's not there. I mean, we have to imagine that it's not there. Obviously, it is there, right? So because you can't see the planet going around, you can still see its effect on the star. So imagine you were just looking at this star wobbling back and forth like this. Let's say this is you over here and you're watching this star. You'll see the star go away from you and then the star will come towards you. See, if you're over here, the star will go away from you now, and now the star is coming towards you. So even though you can't see the planet, you can guess, you can infer that the planet is there just based on the star's wobble. So the star going back and forth. And that's the idea behind it. So what do we do? Well, first of all, we know that the orbiting planet affects the star. And so what we do is we analyze the light from the star, or the spectrum. Now, this is a special kind of picture that scientists can take. So we take the light from the star, we essentially put it through a special kind of prism, and that breaks up the light into its component colors. Now, what it does, if you actually look at a spectrum, it really does look something like this. Like you'll have like a little sort of screen here, and what you'll see, we normally say this right here is called the wavelength. This is the Greek symbol lambda. So that tells you the wavelength. And essentially the wavelength, I mean, this isn't supposed to be a physics class here, but the wavelength essentially tells you the color. So the length of this wave right here, if you could measure that, that tells you the color. So what you do, you see in this star, you break up its light, and maybe you see some different lines. Maybe you see some lines, I don't know, let's say you see a line here, and then you see, let's say, 2 of them here. This is what a spectrum might look like. See here, they've drawn it like this. Now, what's really cool about it is that these lines correspond to individual elements, which means this is so awesome. You can take the light then from a star, break it up into its spectrum, and you can tell what the star is made of. So this particular one, you can say, oh, this particular star, if I saw these lines here, because you know what values these lines sit at, you know what length these sit at. Then you can tell, oh, that star has some hydrogen in it, on the outside of it at least, has some sodium, and has some calcium. So we call these lines. So what we do then is, number one, I mean, we can tell what the star is made of, but the interesting thing for us to detect these exoplanets is going to be to watch these lines carefully. Okay, so we analyze the light from the stars, and we see these spectral lines. That's what these right here are called here. These are called spectral lines. So people who measure this stuff are people who are doing spectroscopy. See? So you're measuring these spectral lines. You're measuring where these sit. Now what's cool is that then if there is an exoplanet, then we look for red or blue shifted lines. And that's again because if this star is going towards you and then away from you and then towards you and then away from you, and this is you on Earth with a telescope, you're going to see this spectrum of the star. You know, if you saw this line here and then you saw these two here, you will see them. Well, this here is wavelength here. And it turns out the things over on this side, this is sort of red over here, and over here is blue. So what this means is that if these lines periodically, let's say at a certain time, let's say when it's coming towards you, this line will actually appear over here. And this line will be over here, and this line will appear over here. In other words, they've been blue shifted. See, so we'll say that they're blue shifted. But then at a time later, these lines, this dark one here will actually appear over here. And these two lines right here will have shifted to the right. So then they will have gone this way. So you see that if we see these black lines, let's say, if we see them periodically go from left to right over time, if you do this versus time here. So over a period of time, you see them go back and forth like this, from blue shifted to red shifted, blue shifted to red shifted. Remember what that tells us. Blue means coming towards us. Red means going away. So the cool thing is that if we see these things happening, then if we see it happening periodically, then we can infer the existence of an exoplanet. So we can say, aha, we know there's a planet here, because this planet is making the star go back and forth. Now, what can we actually infer from this? This is actually really cool. This is a real graph of a real star. Remember before I talked about HD 20948b. So this is a real graph taken from exoplanets.org, which is one of the official places to go look. But you can see this radial velocity graph of it. So this tells you basically its speed, and this tells you, well, phase, but you can also say this is time. So let's assume that this right here, this is time here. So what you can do is you can measure some stuff here. You can actually measure the height of this right here. So, you know, from the middle of this graph right here, this graph goes sort of up and down, tells you it's going, you know, away from you, and then no speed from you, and then towards you, then away from you, then towards you. That's what the radial velocity, the speed of it, tells you. So it's at negative speed, then positive speed. It's like it's going away from you, towards you, away from you, towards you. So knowing this value right here, we call that the amplitude. And don't worry, you don't have to measure this or anything, not for our case. But if you'd like to learn more about it, this is how it's done. We can measure this height here, and we can also measure the time it takes, you know, let's say to go from, we call it period. So maybe from here to here, we would measure that length right here. That's called a period. And by knowing the period, now you could measure the peak to the peak, or a bottom to a bottom, or a middle to a middle. But if you measure this period and the amplitude, it turns out you can infer some stuff from it. What you can infer is actually its orbital distance. So you can actually tell the orbital distance, which is really cool. So what I mean by that is that this unseen planet that's making the star do this, remember, we're only looking at the light from the star, but this unseen planet that's making the star do that, if this right here is my star, now we don't see the planet, okay, so just remember that we actually can't see this planet that's going around here, but what we can infer from this, we can actually tell how far away it is, which is really cool. And on top of that, it turns out you can also tell the mass of the planet. So you can tell the orbital distance of this sort of invisible planet, and you can tell the mass of the planet. You can calculate them. That's all based on this awesome method called Doppler Method. Now, it's actually a very successful method. Most of the exoplanets that have been detected have actually been done using this method here. And in fact, it's very accurate. We can actually get, because you have to be able to tell the difference, you know, between the star moving towards you and away from you. And we're getting close to, so I'm going to put a little squiggly equal sign here, around 1 meter per second accuracy. In other words, we're getting to where we can actually detect a difference in the star's motion of 1 meter per second back and forth. It used to be like 10 or 20, so we're getting a lot better. But one interesting thing is that we have to be within line of sight of this. In other words, if this right here is your star, I'll just draw it like this right here. If this is your star and your planet is orbiting, let's say like this right here, going around like this right here, if that's your planet, you have to be in line of sight. In other words, this has to be you. This is a really creepy eyeball here I'm trying to draw. So this is you sort of looking at it like this. In other words, it has to be sort of in this orbital plane. In other words, if it was like this, I'll just show you an example of what wouldn't really work very well for this method. So because space is in 3 dimensions, sometimes, I mean, orbits can be in any direction here. And this orbit here is kind of like, if you imagine, it's like it's a piece of paper here, you know, like a flat piece of paper here. So this one here sort of follows along this piece of paper. But what if instead it orbits like this right here? Because that's fully possible. So let's say this right here was your piece of paper now instead, like this. So if I rotated it like this, we wouldn't really notice it because this planet would be making the star go this way and this way. So you see, this radial velocity method wouldn't work very well because we wouldn't really notice the star going towards us or away from us. See, over here, it would go towards us and away from us if this is us looking at it. So that's something important here.